times 0.45 cosine theta on 0.595 squared. Now the next thing that we see is that we get omega squared on 2. So what I'll do is, well, when we've integrated the left hand side we get omega squared on 2. I'll just make that omega squared and bring the 2 to the other side. So we end up getting 2 times 9.81 times 0.45 times sine. When we've integrated with respect to theta, we end up getting sine of theta, so sine theta over 0.595 squared. Now when we substitute in sine theta, or theta equals 45 degrees, we end up getting, let me just plug this in, we end up getting omega squared equals 21.5977354, which is roughly equal to 21.6 to 3 significant figures. Okay, so the next thing that we'll do is we'll substitute theta into our alpha equation so that we can solve for our normal and tangential components of acceleration, and thus normal and tangential components of force. To do this, what we have to do is solve for our equations of motion in terms of tangential force and normal force. But the first thing I'm going to do is I'm just going to substitute in theta. Do this in your calculator. I'm going to substitute theta into the alpha equation and just write it down here, and we end up getting alpha equals 8.81723.857, which is roughly equal to 8.82 to 3 significant figures. Alright, now I'm going to do the equation of motion for the tangential component of force. So sum of the forces in the tangential is equal to m radius to the center of mass times alpha, and we could just substitute our values straight in. So from our free body diagram on this page in here, from this free body diagram, we see that the gravitational force in here has a tangential component and a normal component. But what we're looking for at the moment wait a sec. What we're looking for at the moment is that tangential component of force. Because we already know all of these values. So if we go ahead from this free body diagram, oh, not this one, sorry. From this free body diagram here, and this free body diagram here, we'll say G is acting in the opposite direction, so G is negative, so we've got those are O and an OT. Just fix that up. I forgot to label those. My mistake. We end up getting an equation like this for our tangential. We get OT, so it's negative because it's in the opposite direction to the tangent, or the tangential direction of motion. That's plus plus, it doesn't really matter if we use sine or cosine because it's 45 degrees, so they're going to be equal anyway. It should be plus the mass times gravitational, so mg, so 10 times 9.81 times sine, I'll use sine 45 degrees in here, and that's just equal to 10 times 0.45 times 8.82. And then if we solve for our tangential component of force at O, we end up getting OT equals 29, okay, I'll write it down, 29.6896017, which is roughly equal to 29.7 newtons. We should actually, I should go back and label the dimensions or the units of everything. So the next thing I'm going to do is the component of force in the normal direction. And we'll just cross this out. We end up getting we know all these values, but what we have to do is find an equation for those. So what we'll do is we'll go back from that free body diagram again, this free body diagram here on the left, and say our normal component of force, or ON, plus or minus G cosine 45 is equivalent to mr omega squared. So normal component of force minus mg cosine 45 degrees is equal to mr omega squared, and that's the radius to the center of mass again. So our normal component of force ends up getting, we'll take m out as a common factor, so we get g cosine 45 plus r omega squared, and that ends up giving us, what does it give us? It gives us 100, I'll write it down, 166.556985, which is roughly equivalent to 166.6 newtons. Now the final thing we'll do, and I'll just do that up here because I'm running out of paper, is our resultant force. It's our resultant force acting at O. And we just get that by finding the magnitude of O as a force, which is simply square root of ON squared plus OT squared, which is equal to, I'll get you to check this on your calculator, but it's, from what I've got, it's 169.182451, which is roughly equal to 169 or 169.2 newtons. Okay, that's all for this video. Thanks for watching.